All right, welcome to lesson 2 of unit 2. We're going to talk about these things called differential equations today. Hopefully you can know what that is by the end of the day. And differential equations, like all equations, have solutions. And there's two kinds. One is called the particular and one is called the general. So hopefully you'll know what those are and what the difference is between them by the end of the day. And if there's time, we'll also talk about how to find area under the curve. So let's go ahead and jump in and do this thing. All right. So what is a differential equation, first of all? A differential equation is an equation that has a derivative as part of the equation. So if you see a dy dx or a y prime in there, anywhere, that's a differential equation. So that's a differential equation. It could also be an implicit one like this. It doesn't matter. So long as there is a derivative, a dy dx in there, then it's what we call a differential equation. Okay? So, moving along. So, suppose a student had a function, f of x, and they found its derivative, and the result of their work is this. What was the original function? Hopefully you guys know that it would be this. Okay? This is what we would call the solution to the differential equation. So what we did yesterday, right, well, not yesterday, but our last lesson, was we found out how to integrate functions, which is the opposite of finding the derivative, and we ended up with this, which we call the antiderivative. Well, the antiderivative is what's known as the solution to the differential equation. Now there's two types of solutions. There's the particular and then there's the general. So we'll talk about those. Let's summarize what we've learned here so far. So the solution to a differential equation is the antiderivative of that differential equation. So it's funny, I'm just giving you a whole bunch of words that are synonyms, but you need to know the vocabulary because they're going to use this vocabulary. And so you need to know what they're talking about when they use it. So antiderivative is also known as an indefinite integral, which is also known as a solution to a differential equation. All right, and that's that. Pretty straightforward. Now, let's talk about general solutions versus particular solutions. A general solution of a differential equation is a standard antiderivative that contains the unknown constant c. So, for instance, there's my differential equation. The general solution of that would be x squared plus c. We call that the general solution. The word general means like it's not a specific answer, but it's a answer. And the reason why it's a answer is because that c could be anything. So, technically, x squared plus 1 is a solution. X squared plus 2 is a solution. X squared plus 100 is a solution to the differential equation. So instead of putting a specific number there, we just put c, and that represents the general solution. So since I don't know what the c is, then, we kind of don't know what the function is, right? What if I told you that c was 0? In that case, it would be this parabola right here. That parabola is the parabola y equals x squared plus 0, if you want to say plus 0, right? But if we put plus 1, now I've got a new parabola, right? What that does is it shifts the graph up. Or if I were to say plus 3, that would be this one. This parabola is just the same thing. It's been shifted up 3. That's the equation x squared plus 3. So all of these are solutions to this differential equation. All of these parabolas have the same derivative, 2x. So in other words, the slope at x equals 1 will be 2, no matter what parabola you pick. If you pick this parabola, the slope is 2. If you pick this parabola, the slope is 2. If you pick this parabola, the slope is 2. They all have the same derivative. Now, thinking about this in terms of integrals, though, if we call this a differential equation, this is my general solution, And all of these are possible particular solutions to the differential equation. So you probably already know then what a particular solution is. A particular solution is whenever you have enough information to figure out what the C is. What they're going to do is they're going to give you a little bit of extra information, and all you need is one more point. If you know a point that exists on the original graph, then you have enough to figure out which one it is. So let's consider our equation again, y prime equals 2x. But this time I'm giving you something that I'm calling an initial condition, and it's y of 0 equals 3. Now notice this is y, not y prime. So this is the differential equation up here, but this is what the function was before we took the derivative, and this is telling me a point on my graph. This is telling me that the x value is 0 and the y value is 3 on the original function, which is called y, and that function's differential equation is here. Okay, so let's keep all that in mind. I'm providing you with a point, in other words, on the original graph. Now, the particular solution to this differential equation would be y equals x squared plus 3. Now let me explain it a little bit more to you here. We already know how to find the general solution here. The general solution is what you get when you take your differential equation and you integrate it, right? If we integrate this side, we get y. And if we integrate this side, we get x squared plus c. And that's my general solution. But I know something now about this general solution. I know that this solution actually has an initial condition. They're giving me some knowledge about this equation. They're telling me that the x value on this y function is 0 and the y value is 3. So if I were to plug those values in here, I can solve for c. 0 squared is 0. And then c plus 0 is just c, so I'm just going to put c equals 3. And now I know that for my general solution, I don't have to wonder about what this number is anymore. Now I know that it must be 3, and that's because they gave me a point. And so now I have a particular solution. So let's look at that from a graphical perspective really quick. So as you guys might recall on the last slide, when I have a general solution, it could be any one of these parabolas. But now that I'm telling you a specific point, y of 0 equals 3, well, that's this point right here. That's the point 0, 3. And there's only one of these parabolas up here that has that point on there, and it's this guy. So now I'm not talking about a bunch of different parabolas all at once. I'm talking about a specific particular parabola now, and that's because I was given an initial condition. So we have a lot of vocabulary going on here. So let's just review all the vocabulary for now. So if you have an equation with a derivative in it, or a prime, that's what we call a differential equation. When you integrate it to find out what the original equation was, that's called a solution. Now, if you don't know what your constant is, then that's a general solution. But if they give you an initial condition, you can find that C value, and now you have what's called a particular solution. Okay, so that's a lot of vocabulary, but put it on a flashcard and study it. Good stuff to remember that you're going to see that vocabulary as we go along. All right, so example 1. Find the particular solution to the differential equation using the initial conditions provided. Okay, so how do I know that this is a differential equation? First of all, because there's a derivative. So how do you find the solution to a differential equation? You integrate it. So I'm going to integrate both sides of this equation with respect to x. Okay? So when you integrate f prime, I'm not going to put capital F. Now here's why. The reason why I'm not going to do this is because there's a prime next to that F. So if you integrate F prime, you just get regular F. Now if I had just regular F here and I integrated it, I would put capital F. But since there's a prime on it, I'm just going to leave it as little f. Now, over here, we need to integrate this side as well. So we're going to add 1 to the power, and we're going to divide by that power. And then for a constant, you just put an x next to it. And don't forget your plus c. Let's simplify it a little bit. Now, some of you guys may be wondering why I didn't put a plus c on this side. You don't need to. It wouldn't change anything if you did. So you don't need to. Just put it on one side. So this is what we call the general solution. So how do you find a general solution? You take your differential equation and you integrate it. Okay? But now I want to find a particular solution. And that means I need an initial condition. In other words, I need to know a point on this graph. I need to know an x value and a y value so I can plug those in and solve for c. And lo and behold, I have a point on the graph of f. There's my x value, there's my y value, right? So let's go ahead and plug those in. F of 1 is equal to negative 1 squared minus 2 times 1 plus c. F of 1, right, equals negative 2, so I can just replace that whole thing with negative 2 now. And let's simplify the right side. We end up with negative 1 minus 2 plus c. Running out of space here. So if I put these two together, I'm going to end up with negative 2 on the right and the left of me equals negative 3 plus c. Add the 3 on both sides. I've got my c value is 1. So now I'm ready to write my final answer. The particular solution is the same thing as the general solution, except now we know what the c is. The c is 1. And there's my answer. All right, so 3 steps, right? Step 1, integrate. Step 2, plug in your initial condition and solve. Step 3, write your particular solution. Okay, so let's do another one really quick, just to make sure you guys have got the gist of how to do it. So we want to find a particular solution to this differential equation with this initial condition. We'll get to the initial condition later. So step 1, we need to integrate this. I'm going to squish a little dx in there now. There we go. Now on this side, we integrate f prime, you get regular f. On the other side, before I integrate it, I want to rewrite it, because I don't like the way that that's written. There we go. Now I'm going to integrate it. And using the reverse power rule, I'm going to add 1 to my power, and then I'm going to divide by that number. Don't forget your plus c. There's your general solution. Now I don't like negative exponents, so I'm going to go ahead and rewrite this in the following way. I'm going to put the x squared on the bottom with the 2, and also we don't usually leave negative coefficients on the bottom like that. We just kind of put in front of the whole fraction. So I would rewrite that as 1 over 2x squared plus c. Okay. Now let's go ahead and continue. So I've got my general solution right here. I'll abbreviate it GS. But now I want to find my particular solution. So the first thing I do now is I'm going to plug in my initial condition. Now my initial condition is what they gave me in the beginning of the problem. All right, so they told me that I'm plugging in 3 for the f. All right, and f of 3 is 17 over 18. And I'm going to go ahead and just add 1/18 on both sides. which gives me 18 over 18, which gives me 1. So C is 1. And so my final answer here will just take your general solution and replace the C with what you got. So it's going to be negative 1 over 2x squared plus 1. There's your general solution, and I guess we should put f of x equals. Okay, so three-step process. Step 1, integrate. Step 2, plug in your initial condition. Step 3, write your particular solution. Okay, so I'm letting you guys try one of these real quick. Go ahead and do numbers 1 and 2, and when you've unpaused the video, you will see the solutions. Okay, so there's your 2 solutions. Let's see here, what's kind of worth pointing out. I want to emphasize something to you guys. I want you to notice when the integral sign is there and when it's not. So like if you integrate f prime, just a second. If you integrate f prime, you get f. And since I did the integral, notice the integral's gone. But from here, I didn't integrate. I just changed the way it looked. I didn't like the 2 on the bottom, so I moved to the top. That's not integration, so the integral symbol's there. But notice when I get to this next step, the integral symbol's gone because I applied the reverse power rule, right? The integration power rule. So I integrated it. And so now the integration symbol's gone. So pay attention to that kind of stuff because that does matter. You don't want to have your final answer still have an integral on there because I see students leave that there all the time. It's once you take the integral, get rid of it. Okay? All right. So there's that. All right, so what good are integrals anyway? What's the point of working backwards? What's the point of finding an antiderivative or a general solution is another way of saying it? Well, integrals are a way of, but here's a general answer. I mean, an easy answer is it helps you find area under a curve. But more generally, what integrals do is they're a great way to add up an infinite number of infinitely small things. Okay, so what do I mean by that? You guys remember how at the beginning of this unit I gave you guys a little worksheet where we estimated the area under the curve using rectangles, right? And one of the things that we discovered is that the more rectangles you use, the more accurate your answer is. And so you guys can imagine that if the skinnier and skinnier I make these rectangles, the more it's going to become just like the actual area under the curve. And so what if there was a way I could let the width of these rectangles become infinitely small, and that would, as a result, that would actually give me the exact area under the curve if I could let those rectangles become infinitely skinny, like they're just a straight line. Okay? Now, if I made them infinitely skinny, that means I could fit infinitely many of them underneath of that line, right? So that's a weird thing to wrap your brain around, but guess what? That's exactly what an integral does. An integral is where you are adding together an infinite number of infinitely small values, and it gives you a total answer. Okay? So it takes away the approximation and makes it become an exact answer. So that's what integrals do. Okay? So let's talk about this rule here. It's called the fundamental theorem of calculus. And what it is basically is it's how to find the area under a curve. Okay? Now, you might notice from the name here that this is probably a pretty important rule. It's the fundamental theorem of calculus. So it's something you definitely want to commit to memory. So let's say I wanted to find the area under this curve. Okay? So we have this line here. The curve is y equals f of x. And I want to find the area from x equals a to x equals b. And that capital A represents the area, right? Well, here's how you do it. Now, why does this work? We're not talking about that right now. We're just talking about the fact that it does work. Okay? So you're going to integrate the function f of x. Now you'll notice that I put the b in the, there's something new here though, right? Our little integral symbol, it has the lowercase b and the lowercase a there. Those are the x values, the starting point and the ending point. Those are what we call the limits of integration. The upper limit of integration and the lower limit of integration. And notice this is what we call a definite integral. A few lessons back, I guess it was just one lesson back, we talked about the indefinite integral. That's when there's no numbers here and you're just undifferentiating it. You're just finding the antiderivative. But in this case, we're going to do a little bit more than that. We're going to undifferentiate it, but we're going to do more, and it has to do with these b and a here. And what it's going to do is it's going to tell me the area under the curve, and that's what we call not an indefinite integral, but a definite integral. Okay? So when you have numbers on your integral, that's what we call a definite integral. And what it does is it helps you find area under the curve. Now, how does it work? Well, the first thing you're going to do is you're going to integrate your integrand here. So the little f is going to become big F, right? But then what we're going to do is we're going to plug in the b and the a into the big F and little f and subtract them. And somehow, believe it or not, that tells you the area under the curve. Why does that work? Well, we don't get to know why. For right now, for us, it just seems like witchcraft and voodoo, and it happens to work. But there's a reason it works. But for now, that's it. So this is what we call the fundamental theorem of calculus. Definitely a little formula you want to have in your brain. So the trick here is integrate, plug in your b, plug in your a, and subtract. Okay? 3 steps. Integrate, plug in b and a, subtract, and you get the area under the curve. It's magic. So let's go ahead and see if we can make this work for us here. All right? So I'm going to use the fundamental theorem of calculus to find the area underneath of this curve. Here we go. So I'm going to integrate my function, which is 4x. I'm going to leave the y off for now. We don't need it. I'm going to integrate my function, and I want to start at 0 and end at 4. So I want to find the area from x equals 0 to x equals 4, and that's where they go. Okay, so the first thing I'm going to do is I'm going to integrate this. Okay, so it's going to be 4x squared over 2. Now, some of you guys might be saying, wait a minute, Mr. Bay, you forgot your c. I did not. I did not forget my c. There's a reason I left it off. I don't want to confuse you right now with my explanation. But for now, just so you guys know, I'm not going to put the c, and you don't need to when you're doing definite integrals, okay? So for now, just follow my lead. So we integrate, and we put the 0 and 4 there. We don't need the c. All right, I'm going to simplify this because it's a little bit ugly. Now, step 1, integrate. I guess I can make my arrow go down farther because this is where it stops. So step 1 is to integrate. Now, I want you guys to notice some notational things. After I integrated, I don't have my integral symbol anymore. It's gone, right? But you'll notice I have these brackets instead. That's just the notation that we use. So instead of having the 4 and the 0 on the integral, now they're on these brackets. Okay. Now, step 2 is you're going to plug in both of these numbers for x. And then you're going to subtract those. Okay? So step 1, integrate. Step 2, plug in your limits. Step 3 is to go ahead and simplify this. So we end up with 2 times 16, which is 32, minus 0 is 32. What I just found there, what does that number represent? That's the area under the curve from x equals 4 to x equals 0. Now this is the calculus way of doing it. And this is how we're going to do it. But I deliberately chose this one because I wanted to show you guys something interesting about this. Because this one you can actually do with geometry. All right? So, it's just a straight line. So that's pretty easy. Let's plug in 0. If I plug in 0, what do I get? 0. So if I plug in 0, I get 0. What about if I plug in 4? What do I get? I get 16. So I'm going to plot those 2 points, 0, 0, and 4, 16. I'll count by 2s on the y-axis. 2, 4, 6, 8, 10, 12, 14, 16. That way I don't run out of space. Now what I want to do is I want to find the area from here at 0 to here at 4, and it's a triangle. Okay, so we already found the area using calculus, but I want to show you that using geometry, we're going to get the same exact answer. So check this out. What's the base of my triangle is? 4. What's the height? It is 16. So base times height is how you find the area of a triangle, and you divide it in half, right? Well, this is 64 divided by 2 is 32. It's the same answer. Okay, so I found it using geometry. So why is the calculus method better? Well, because if I were to put a square on here, it's not a straight line anymore, and you can't do it using geometry. So calculus works for any line. Geometry only works for straight lines. Okay? So I think we better do another one, though, just to make sure that you guys have the idea, because this could be a little bit overwhelming. Let's do another one here real quick. I'll come back to those in a second. Let's do, I'm going to make one up, because I feel like there's a lot there. Okay. Actually, we'll start off the same way. Let's say, find the area under the curve y equals 9x squared from, let's say, 0, x equals 0, I should say, to x equals 2. Let's find the area under the curve from x equals 0 to x equals 2. All right, step 1. Integrate the function. Put your limits of integration on there. If I integrate that, I'm going to get x cubed over 3. And now I don't have the integral symbol anymore. I've got brackets. And I put my limits of integration there. Simplify it a little bit. And that's the end of step 1. So step 1 is integrate. Step 2 is to plug in your limits. To each one and subtract them. Step 3 is to simplify it. So this is 8 times 3, which is 24. And this is 0. My answer is 24. So the area under the curve would be 24. What would this look like? You don't need to draw this, but if you graphed 9x squared, it's going to be like a really skinny looking parabola. Okay? And what we just found was the area from 0 to 2. So it's almost like a triangle, but it's bending, it's curving, so it's not really a triangle. So we just found this area here under that parabola, which is 24. Okay? So step 1, integrate. Step 2, plug in. Step 3, simplify. Tells you the area under the curve. All right? So I want you guys to be trying one of these now. Zip up to where we were. I kind of lost my place. Just a minute. There we go. All right, so there's the one for you guys. I want you guys to go ahead and pause your video and give that one a try. When you unpause it, you will see the solution. I just realized I forgot to give you guys some numbers to work with here, didn't I? So find the area under the curve from x equals, let's say, 3 to x equals 5. From x equals 3 to x equals 5. Okay, there you guys go. Should have gotten negative 48. Now, a couple of things that I'll say here that I actually didn't say, I probably should have, is that where you put the limits matters. You're supposed to put the smaller one on the bottom and the bigger one on the top. So 3 goes on the bottom, 5 goes on the top. Okay? So there's that. It's pretty self-explanatory. I think the rest of it's pretty obvious. Another thing is all the ones I had, I started with 0 down here. But I gave you guys 3, so you actually ended up having 2 numbers to combine. That's another little difference. Not a big deal, though. But something else that's odd is the answer. Look at that answer. That's a negative area. What does that mean? How could you have a negative area? Well, that has an interpretation, and I'll show you. Let's graph this function once again from 3 to 5. Okay? So, you don't have to do this if you don't want to, but it's just to help you understand. So, we have 2 x values, and I need the y values to go with them. So I'm going to plug 3 in to my function. That gives me negative 18. And then I'm going to plug 5 into my function. That gives me negative 30. Okay? So 1, 2, 3, 4, 5. And for the y-axis, I need to go all the way down to negative 30. So I'm going to count by 5s. 5, 10, 15, 20, 25. Kind of running. Won't even let me write down that far, but there it is. Okay. So I'm going to graph the point 3, negative 18, which would probably be like right about here, and the point 5, negative 30, which would be down here. And then I'm going to connect those dots. And what I'm doing is I'm finding the area under the curve. Now, that's actually kind of a wrong way to say it, because what I mean by under the curve is I mean from the line to the x-axis. So it's kind of like a little trapezoid that I'm finding the area of right now. I don't want to say under, because how far down does that go? Well, that goes down forever. So you can't find the area under the line there. So what the integral tells you is not necessarily the area under the curve. That's how we say it in calculus all the time. But what we really mean is the area between the line and the x-axis is probably a better way of saying it. Now, why would I call this a negative area? Well, because it's under the x-axis. Anytime you have an area that's under the x-axis, it comes out negative. Okay? So really, the true area is 48. That's what the area really is. But the fact that it's negative just tells us that it's under the x-axis. So, there's that. Let's go ahead and move on to our last slide. We're not going to do anything with it. It's just a conversation piece. So, let's say that I have a curve that goes from here to here, and I ask you to find the integral from here to here. Well, some of it is above the x-axis. That would be a positive area. And some of it's below the x-axis. That would be a negative area. And the total area is what you would get if you added them together. Okay, well, if you're adding a positive number to a negative number, you're actually going to be subtracting them, right? And so basically, whichever one's bigger wins. Now, if you want to find the literal area, you would ignore the negative here. And you would have to find the area from here to here, and the area from here separately. Change this one to a positive and then add them together. That'll tell you the positive area. But if you don't do that, you'll end up with the difference between those two areas because one's above and one's below. Getting a little bit ahead of ourselves there. All that I really want you guys to know, though, is that area above is positive, area below is negative. So that does it for our lesson today. So today, just, you know, if you're interested, we did a couple of things today, and they were quite different. So we talked about what differential equations are. Differential equations are equations that have a derivative in them. The solution to a differential equation is basically the antiderivative. Now, when your antiderivative has a c in it, we call that a general solution. But whenever you have an initial condition and you can find out what c is, we call that a particular solution. So we practiced finding particular solutions when I gave you a differential equation and an initial condition. The next thing we moved on to is talking about how integrals actually help you find the area under the curve. Okay? The area under the curve can be found by using the fundamental theorem of calculus, which basically tells us that if you take the integral of something, you plug in the limits of integration and subtract them, you will end up with the area under the curve. This is what we call a definite integral when you have numbers on the integral symbol, and it tells you the area under the curve. And then we went ahead and we applied that rule. We also saw that area above is positive, area below is negative, and that's where we stopped. I'll probably mention it again in a future video, but now some of you guys might be wondering, Mr. Bailey, why? There's one question I haven't answered yet. And the question I haven't answered is, why don't we do the C with definite integrals? So I'll answer that question for you now. The reason we don't do the C is simply because we don't have to. The C kind of cancels itself out. So for instance, suppose I had this, right? The integral of 2x. And I wanted to go from 1 to 5. Okay. Well, let's go ahead and integrate that. But this time I'll put the C in there, okay? I'll just put the C in there. So we have our integral, and I included the C. The next thing we do after we integrate it is we plug in the stuff, right? So I have 5 squared plus C minus 1 squared plus C. So we have 25 plus C minus 1 plus C. And when you distribute the negative, look what happens here. You had a C here, you had a C here, and you're subtracting it. So basically the C's cancel each other out. They never matter. So when you're doing a definite integral, since you end up subtracting, the C cancels, so it doesn't even really matter. So you don't even need to bother including the C when you do a definite integral. Now, if you want to do it, you can. You might end up making a mistake, though, if you include it, just because more work makes more likelihood of making a mistake. But the point is that when you do a definite integral, when you're trying to use the fundamental theorem of calculus to find area under a curve, you don't need to use a C. If I ask you to find a particular or general solution, you do need to use a C. All right, and that concludes our lesson for the day.